Question A. In initial state, there is no titration occur. So, KOH will completely dissociated in water and produce ion K+, ion OH-, and H2O. As KOH is completely dissociated in water, so the concentration of KOH will have the same value of with concentration of OH-, which is 0.2 molar. Okay, first we find POH using negative log. So negative log 0.2, you will get 0.699. To get pH, 14 minus 0.699, then pH will get 13.30.
First, we need to find the number of mole of HF, which is 5 times 0.4 divided by 1000 equals to 2 times 10 power of negative 3 mole. Next, we find the number of mole of KOH, which is we got 8 times 10 power of negative 3 mole, and then we put it in the ICF table. So, the equation is KOH plus HF equals to KF plus H2O. So, we put in the number of moles, and the changes is 0.002. We minus it at the reactant and plus it at the product. So, at the final, we will get 0.006 at KOH and 0 at HF. And at KF, we got 0.002 as the number of moles. So, we put the KOH as in the equation. That is KOH plus H2O equals to K plus H2O plus OH minus. Which, okay, the KOH we got is 0.133 as the concentration. That is, concentration equals to number of mole divided by volume. So, we got 0.133. This is a complete dissociation. We will get the number of mole of KOH and OH minus is the same. So, we put the concentration of OH minus into the formula. POH equals to negative log 0.1333, and we can get it is as 0.875. So, the pH is equal to 14 minus 0.875, and we got the pH as 13.12.
Okay, so for question C, it asks us for the midpoint of the titration. So as usual, when the volume became additive, we have to use mole. So N of KOH is 8 times 10 to the power of negative 3. And for midpoint of the titration, it must be M1 V1 equals to 1 over 2 M2 V2. So the half for NKOH is 4 times 10 to the power of negative 3 mole. So, like usual, we build an ice table for the use of mole for KOH and HF. So, just build it, and for the initial, put the mole for KOH is 0.008, HF 0.004, and the product is 0. And the change is, since HF is the limiting reactant, so we minus 0.004 from each reactant, and at the product we plus 0.004, and we get the final like this. So the remaining product in the beaker is the KOH and the KF, and since the KOH is a strong base, so the pH will be determined by the concentration of KOH. So the KOH will dissociate with water, and since it is a complete dissociation, the concentration is the mole is the same for the product and the reactant. So we have the mole of OH minus is 0.04. So we switch the mole into the concentration, and you get the concentration of OH minus is 0.1 mole. And to get the POH, just apply the formula of negative log 0.1, and you'll get 1 as POH. And for the pH, just subtract 14 with 1, and you get the pH as 13.
So for the next question, we need to find the equivalence points of this titration. As we know, at equivalence points, the number of mole is the same. So we use the formula of M1V1 equals to M2V2 as the number of mole is same. So we plug in the M1V1 is the KOH. So we plug in 40 milliliter times 0.2 molar, and V2 we does not know how much is it. So we need to find it, and we put the concentration of HF at 0.4 molar. So we can get the volume of HF is 20 milliliter. So next we need to find the number of moles. The number of moles is the same, so we use the number of moles of KOH, and we plug in the numbers as 40 divided by 1000 times 0.2, and we can get the number of moles is 8 times 10 power of negative 3. So we must find the concentration of KF first. So to find the concentration of KF, we use the normal equation, that is KF concentration equals to number of mole divided by volume, and we get 8 times 10 power of negative 3 divided by 60, which is the total volume in the beaker, divide by 1000 to get liter, and it will be equal to 0.1333 molar. From the KF, we find that F negative is a strong conjugate base that is derived from the weak acid. So the F negative will further react with water to form HF and OH minus. So we drew a ICE table and ICF table to find the concentration of OH minus. So we plug in 0.1133 molar of F negative as the reactant concentrations, and at the product side we put 0 and 0 first because there is no concentration happen. So at the changes we put negative X at the reactant because we does not know how much it is being used, and plus X at both HF and OH minus. Okay, then at the final we can get 0.133 minus X as the F negative concentration, and X at both HF and OH minus. We use the formula of Kb equals to product over reactant. So the Kb is 1.47 times 10 power of negative 11 equals to X to the power of 2 divided by 0.133 minus X. So the X is small, so it is negligible. So we calculate the X and we get X, that is the concentration of OH minus, equals to 1.4 times 10 power of negative 6 molar. So we use the formula of POH equals to negative log concentration of OH minus, and we get POH equals to 5.85. So to find the pH, we just need to subtract 5.85 with 14, and we can get 8.15 as the pH.
The number of mole of KOH is 0.008 mole, and the number of mole of HF is 0.016 mole. So we use the ICF table to count the final mole of HF and KF. Since the lower mole is 0.008, so you minus 0.008 at KOH and AHF, and plus 0.008 at KF, and then you get 0.008 mole for the final mole of HF and final mole of KF. And then you change the number of mole into concentration, so you get 0.1 molar, and then we use the Ka given to find the pH, which is by using the pH equals to pKa plus log of conjugate base over weak acid, and then you just plug in the information that you have, which is the Ka, and then you get the pH, which is 3.17.